Section 12.3, Velocity and Acceleration. So in this section, we're going to be applying the differentiation and integration that we were seeing in section 12.2. And specifically, we're going to be doing this in a physics setting with velocity and acceleration. So we begin, of course, with our position vector. This gives us our position in the plane or in space, depending on if we're in R2 or R3. So that's given by R of t, which is going to be equal to x of t in the I direction plus y of t in the j direction plus z of t in the k direction. Okay, and of course, if we're working in 2 dimensions, there will not be a k component, and if we are working in 3 dimensions, there will be. Then the velocity vector is the derivative. So we'll call this v of t. That's equal to r prime of t, which is equal to x prime of t in the I direction, y prime of t in the j direction, z prime of t in the k direction. Okay, and this is going to give us our instantaneous velocity at t. All right. And the acceleration vector is, of course, the derivative of the velocity vector. So the acceleration vector, we'll call it a of t, is equal to v prime of t, which is, of course, the second derivative of r of t. And it's equal to the second derivative of each component, x double prime of t in the I direction plus y double prime of t in the j direction plus z double prime of t in the k direction. Okay. Oh, and one more thing, velocity, if you find the magnitude of the velocity vector at t, you find the speed. So the magnitude of v of t is equal to the speed at any given t. Okay, so we are going to use these to find velocity and acceleration vectors, to find the speed. We're also going to use it to solve for position vectors. So given an acceleration and some point, we'll be able to work our way backwards to find the position vector. So we're going to do all of these things. Let's begin with an example. So suppose I give you r of t is equal to 2 sine of t over 2 in the I direction plus 2 cosine of t over 2 in the j direction. Okay. So suppose this is giving you the position of a vector, giving you the position of a particle in motion along a curve. Let's find the velocity vector, the speed and acceleration, for this curve. Okay, so the velocity vector is, of course, r prime of t, which is going to be equal to cosine of t over 2. Okay, so we had a 2 in front, and the derivative of sine is cosine of t over 2, and then we chain on the derivative of t over 2, which is 1/2, which cancels with that 2. Okay, so that's our I direction, plus 2 times negative sine of t over 2, chain on 1/2, and that's in the j direction. So our velocity vector is equal to cosine of t over 2 I minus sine of t over 2 j. Okay. Now we can find the magnitude of that to determine the speed. So our speed is the magnitude. So that's going to be cosine of t over 2 squared plus negative sine of t over 2 squared, square root. So that's the square root of cosine squared t over 2 plus sine squared of t over 2. Sine squared plus cosine squared is 1. Square root of 1 is 1. So the speed is constant. The speed is equal to 1 at any point on this curve. And then the acceleration is, of course, the derivative of the velocity. So that's going to give us negative 1/2 sine of t over 2 in the I direction minus 1/2 cosine of t over 2 in the j direction. Now, I'm assuming you guys already know how to do these antiderivatives, so if you do have questions about it, though, please do let me know. I'll be happy to go over the details of that with you. Okay. All right, so now let's take a look at another example. All right, so this time we are going to work in R3, and we're going to sketch the path. So let's sketch the path of an object moving in space along the curve C given by R of t equal to t in the I direction plus t cubed in the j direction plus 3t in the k direction. Okay. And find its velocity and acceleration vectors when t is equal to 1. There we go. Okay, so we have our curve. First thing we want to do is we want to sketch that. So we've got r of t. I'm going to rewrite it down here. So that's equal to t cubed 3t. So x of t is t, y of t is t cubed, and z of t is 3t. Okay. So we can go ahead and find some points on this curve so we can get it sketched. So let's see here. So we need t, x, y, and z. So let's choose -1, 0, 1, 2, see what we get here. So plugging in -1 for each of these functions, we get -1, -1, -3. Plugging in 0, we get 0, 0, 0. Plugging in 1, we get 1, 1, and 3. Plugging in 2, we get 2, 8, and 6. So let's see what that looks like for us. All right. So the first point is -1, -1, -3. So we go -1, -1. I shouldn't put the point there just yet, because from this point here we go down 3. Okay. So that's the point -1, -1, -3. Then of course we have our point at 0, 0, 0, 0, 0. Then we have the point 1, 1, 3. So we're going to come out 1, over 1, and up 3. So that'll put us at this point here. And then 2, 8, 6. So come out 2. 8 will be out this way. Put us about here. And then up 6. Approximately here. So our curve is, let me erase this. This isn't actually a point. It was just a marker. So then our curve is kind of coming this way. To here, and then around, and then out to here. All right. And the motion is in this direction. Okay, and then we were asked to find the velocity and acceleration vectors when t is equal to 1. So we need to find v of t and a of t, and then we can find out what those are when t is equal to 1. So v of t is, of course, the derivative of r. So that's going to be 1, 3t squared, 3. Then the acceleration vector is the derivative of that, which is 0, 6t, 0. Okay. So the velocity vector at 1, so when t is 1, we're just plugging in 1. It's going to be 1, 3, 3. Okay, so I just substituted a 1 in for t. And then the acceleration vector will do the same. Plug in a 1, so we get 0, 6, 0. And there are our vectors at that point. All right, so now let's do an initial value problem. So example, an object begins moving from rest at the point 1, 2, 0. The acceleration is given by a of t, there we go, a of t, equal to j plus 2k. Find the position vector. The position vector function. Okay, so here's what we know. We know that the acceleration vector is equal to the derivative of the velocity vector, which is equal to the second derivative of the position vector. Okay, so we're going to work our way backwards towards this position vector. So the first thing we're going to do is we are going to find the velocity. So the velocity is going to be equal to the antiderivative of the velocity, of the derivative of the velocity, integrated with respect to t. Okay, so that's going to be the integral of a of t integrated with respect to t. So that is the integral of j plus 2k dt. Okay, so both of these are very easy to integrate. So this is going to become t in the j direction plus 2t in the k direction plus some vector c. So again, I want to remind you, when you are integrating a vector valued function, the constant we are adding is a constant vector, and we must denote it as a vector. Okay, so we need to keep going, but first we need to figure out what is c. What's our clue for that? Well, we were told that our object began at rest. So we know that v of 0 is equal to the 0 vector. So we know that 0j plus 2 times 0k plus c is equal to 0. So that means that c is equal to the 0 vector, which means that our velocity is just equal to tj plus 2tk. Okay, so then our position vector is going to be the integral of this. So r of t is going to be equal to the integral of v of t, because v of dt, because v of t is just the derivative of the position vector. So that's going to be the integral of t in the j direction plus 2t in the k direction dt. So that's equal to 1/2 t squared j plus t squared k plus some constant vector c. And if you'd like, you can differentiate this from the previous constant by putting a little 1 next to it. So anytime you need more than 1, you can always do that. All right, so now we need to figure out what is c. Well, we were given the clue that our initial position was 1, 2, 0, the point 1, 2, 0. This means that our initial position vector was the vector 1, 2, 0. That's how we would have gotten to that initial position. Okay, so we know that 1/2 times 0, let's put this in here, r of 0. There we go. 1/2 times 0 squared in the j direction plus 0 squared in the k direction plus our constant vector c1 is equal to 1 in the I direction plus 2 in the j direction plus 0 in the k direction. So that means that c is equal to 1, 2, try that again, 1, 2, 0, and then we can add that in. So r of t is 1/2 t squared in the j direction plus t squared in the k direction plus 1i plus 2j plus 0k. Okay, so then r of t is equal to I plus 1/2 t squared plus 2 in the j direction plus t squared in the k direction. And there is our final position vector. Okay, so let's do a little physics problem then. So Newton's second law. It's F is equal to ma. Force is equal to the mass times the acceleration. So A is our acceleration. M is, of course, the mass, and F is the force. Okay. So on Earth's surface, every object having mass experiences an acceleration due to gravity. So we can write that as F is equal to negative mg in the j direction. So our acceleration here is g in the j direction, and it's negative because we orient y as to be negative and going down and positive going up. Okay, so then of course force is F and M is mass again, and that g is equal to about 32 feet per second squared, or it's equal to 9.81 meters per second squared. And again, those aren't exact, but they're very good approximations. Okay. All right then, so here's the problem. Suppose a projectile is launched from initial position r0 with initial velocity v0. Find the position vector, goodness sakes, position vector as a function of r0 and v0. Okay, so what do we know? Well, we know that a of t is equal to negative g in the j direction. That's our acceleration. And we know that that's equal to the derivative of our velocity vector, so we can find v of t by taking the antiderivative. So the integral of negative g in the j direction dt. So that's going to give us negative gt in the j direction plus some constant vector c1. All right, so what we know is that the initial velocity is equal to v0, which is equal to, plug in a 0 for t, 0 in the j direction plus c1. So c1 is equal to v0. Right? Okay, so then v of t is equal to negative gt in the j direction plus v0. So we integrate again to get r of t. dt. Okay, so the antiderivative of negative gt is going to be negative 1/2 gt squared in the j direction. And because v0 is a constant vector, each component would simply be multiplied by t, which we can represent as v0 times t. All right, plus a constant vector, I'll call this one c2. And here's what we know. We know that initial position is equal to r0. So if we plug a 0 in for all of the t's in r of t, we get 0 in the j direction plus 0 plus c2. So we find that c2 is equal to r0. So then r of t is equal to negative 1/2 gt squared in the j direction plus v0 t plus r0. Great. But g, negative g in the j direction is equal to a. So this becomes not negative, Let me write this down here. So let me erase that, go away. Okay, so we know that acceleration is equal to negative g in the j direction, and so what we end up with here is that r of t, that is a vector, is equal to 1/2 a t squared plus v naught plus, v naught t, excuse me, plus r naught. And there we have it. Position vector as a function of its initial position and initial velocity. Okay, so we've got that. Now we're going to start looking for v naught and r naught. So let's take a look here. If I have a projectile being shot at some initial height, h, from some initial position, call it r naught, at some initial initial velocity vector, v naught, okay, then it's going to, at the very beginning, start to follow that path v naught, but acceleration due to gravity is going to kick in, and it's going to drop back down and follow a typical parabolic projectile motion curve. Okay? All right, so if we were to break this down, we see that we can take v naught and break it down into its horizontal and vertical components. Okay, so we have this angle theta that the vector v naught forms with the horizontal x-axis, and we're going to break this down. So we need something in the I direction, something in the j direction. So how do we break that down? Well, think about the unit circle. Remember, every point on the unit circle is cosine theta, sine theta. And if it's a bigger circle, it's just the radius of that circle times cosine theta, sine theta. Remember, x is equal to r cosine theta, and y is equal to r sine theta. And that's how we're going to break this up into its component vectors. Okay, so we have x here being equal to the radius, which is the magnitude of v naught, times the cosine of the angle theta. So let's call the magnitude of the vector v naught just v naught, just a constant v naught, cosine of theta. And y then, the y component here, is going to be the magnitude of v naught sine theta, or v naught sine theta. Okay then, so our position vector r of t becomes 1/2 times the acceleration times t squared plus the vector v naught, which is v naught cosine theta I direction, plus v naught sine theta in the j direction, times t, plus r naught. Try that again. Plus r naught. There we go. Okay, and then what is r naught? Well, r naught is straight up from the origin, so r naught is just going to be the initial height h in the j direction. Okay, so this is going to be r of t is equal to 1/2 times a t squared plus v naught cosine of theta t in the I direction plus v naught sine of theta t in the j direction plus h in the j direction. And of course we know the acceleration, that's negative 1/2, that becomes 1/2 times negative g, so I'll put the negative in front, negative 1/2 g in the j direction, t squared. Let's put that t squared on the inside of that, shall we? T squared in the j direction, okay, plus our v naught cosine theta t in the I direction, v naught sine theta t in the j direction, plus h in the j direction. And so what we get is that r of t is equal to v naught cosine of theta times t in the I direction plus h plus v naught sine theta t minus 1/2 gt squared in the j direction. And this is actually the result of theorem 12.3. Okay, this is going to be our position vector for any projectile launched from an initial position, an initial height h, with an initial speed v naught at the angle of elevation theta, neglecting air resistance, where g is the acceleration due to gravity. Okay, so let's go ahead and use this in an example. All right, so suppose Jean kicks a ball on a table 3 feet above the ground. At an angle, at a 45-degree angle, with initial velocity 80 feet per second. A, find the maximum height of the ball. And B, will the ball clear a 10-foot wall 200 feet away? In other words, will it go over a 10-foot wall? Will the ball go over a 10-foot wall 200 feet away? Okay, so let's identify everything that we were given. We were given that V naught is 80. That's its speed at that moment. We were not told, the vector. We were given the actual speed, so 80. We know that theta is 45 degrees, or pi over 4. And we know that the initial height is 3 feet. So the initial height h is 3 feet. So let's plug all of this into our formula so that we can get our position vector. So r of t is equal to v naught, which was 80, times cosine of pi over 4, t in the I direction, plus h, which is 3, plus v naught, which was 80, times sine of pi over 4 times t, minus 1/2, we're in feet here, so we should stick to 32 feet per second squared, 32 feet per second squared times t squared. So that's the g from above. Here, I'll circle it in green. That g I'm replacing with 32 feet per second squared. Okay, and that's in the j direction. Okay, so we can simplify this. We have 80, the cosine of pi over 4 is root 2 over 2, and the t times t in the I direction, plus, 3 plus 80 times root 2 over 2 times t minus 16 t squared in the j direction. We simplify a little bit more. We get 40 root 2 t in the I direction plus 3 plus 40 root 2 t minus 16 t squared in the j direction. Okay, so now we need to find that velocity vector so that we can find where it stops moving up and begins to come down. That'll be the maximum height. So when the velocity's vertical component is 0. So v of t is, of course, equal to the derivative of r of t. So that's going to be 40 root 2 in the I direction plus 40 root 2 minus 32t in the j direction. So when is that vertical component equal to 0? Well, that's when 40 root 2 minus 32t is equal to 0, or when 32t is equal to 40 root 2, divide by 32, and we get 5 root 2 over 4. So that is the t value where we reach our maximum height. So we'll now plug that into the position vector to find out what is that maximum height. Okay, so I'm going to go ahead and circle the position vector just so I don't lose track of it. There we go, and I know what I'm plugging into. Okay, so r of 5 root 2 over 4 is equal to 40 root 2 times 5 root 2 over 4 in the I direction plus 3 plus 40 root 2 times 5 root 2 over 4 minus 16 times 5 root 2 over 4 squared in the j direction. Okay, so this simplifies quite a bit. Root 2 times root 2 is 2, so that's going to be 100 in the I direction plus, okay, so we have 3 plus 100 minus, so 4 squared and 16 will cancel, and that leaves me 25 times 2, which is 50 in the j direction. So that's 100i plus 53j. So the vertical component of that would be 53, so our max height will be 53 feet. Okay, so the second part of this question asked us to determine if the ball's height would be at least 10 feet whenever the horizontal distance is 200 feet away. So we need to find the t that will cause the horizontal component to be 200. Okay, so let's go back up here and get r of t. So r of t is equal to 40 root 2 t in the I direction, plus 3 plus 40 root 2 t minus 16 t squared in the j direction. So we need to know, when is 40 root 2 I equal to 200 feet? No I. We just need 40 root 2 t. So sorry about that. 40 root 2 t. There we go. When is that equal to 200? Well, we just divide. So t is equal to 200 divided by 40 root 2. So 40 goes into 200 5 times, and that'll be over root 2. We can rationalize the denominator if we so choose. So that would be 5 root 2 over 2. Okay, so we plug that in and we find the height. So r of 5 root 2 over 2 is 40 root 2 times 5 root 2 over 2. That's the I direction, plus 3 plus 40 root 2 times 5 root 2 over 2 minus 16 times 5 root 2 over 2 squared in the j direction. Okay, all right, so we need to know, is this j component, is that going to be at least 10 feet? So let's see, what is that? 3 plus 40 root 2 times 5 root 2 over 2 is going to be, what, 200? Yes, and then minus 16 divided by 2 squared would be 4, so that's 4 times 25 times 2. So 4 times 25 would give us 100, times 2 would be 200, and that's equal to 3 feet. So the answer is no, it will not clear the 10-foot wall, because it's only going to be 3 feet off the ground at that point. Okay, so I think that'll wrap it up for this section. As always, if you have any questions, please let me know.